Yeah. Okay, so hi everyone. So it's our last day on Zoom, hopefully. We haven't heard anything from the administration, right, about not going back into the classroom next week? Okay, good. Sometimes I miss an email or something. All right, so a couple logistical things first. Let me share screen. So here is our Blackboard, right? And now you'll see this link to Gradescope on the left. And so this is where you'll submit your problem set. And this looks different from your end because this is the instructor view, but you should see something like this where you have like problem set 1 and when it's due on there, right? And if you, so you'll just click on that and you'll click on the problem set and you'll see that it's due. Actually, if I go back to the problem set page, I think you could even download the problem set from Gradescope. Like it's here, right? It's right there on the, on the schedule page. It's right there. And I think you can download a copy of this on Gradescope also if you want. So you can access the problem set directly there. And just a few things, like I think if you read these instructions down here, like I ask you to please upload a PDF. It gives you the option of PDFs or images, and it handles PDFs more nicely, and it makes life easier for the graders. And pretty much any scanning app will let you like export to PDF. So I would just appreciate if you do that. And then I think actually, right, and I said some stuff down here. I don't even know if I have ever said this explicitly with you guys, but like, I certainly, sorry, this is off topic from Gradescope, but on a side, but I do encourage you to work with each other, with other students in the class. I strongly recommend that when you like write up your solutions, you do that on your own, because that's really where a lot of the learning happens, is putting things into your own words and writing things down in your own way. And I do ask at the top of your problem set, if you did work with students, just to like list them, just because that's kind of like an academic honesty sort of thing, right? So sorry, that was an aside. So just, yeah, I mean, this will be on every problem set page. All this stuff will be here, which eyes will start to gloss over, but at least read it now carefully so you see what I'm sort of looking for. And then, and I think at the top of the page up here, actually, there's this thing, and I don't think I said this to you guys. Sorry, I've got 3 different classes, so I'm trying to remember what I said to who. But that there's this, once you upload your PDF, it asks you to assign problems to pages, or assign pages to problems. So like, here, like if we look at the problem set, we'll have like 12.1 number 44, and it'll be like, it'll basically say like, you can click on that and then click on the page that your answer's on, page or pages that your answer's on. And so like, what that means is that the system knows like where your answer to 12.1 number 44 is. And that's helpful because the way the graders and I will grade stuff is it grades in parallel. Like we'll grade all the students like 12.1 number 19, then all the students 12.1 number 44, so that we're grading like all of one problem. And then when we click through the system, it's like it actually pops right up with your answer if you've assigned the pages. And if you haven't assigned the pages, which you can sort of skip that step, it doesn't force you to do it when you upload your problem set. It just comes up as like the student didn't select pages, and then we have to click through the pages of your problem set to like try to find your answer. And it's tedious, and the graders don't get that many hours to grade, and anything that adds to the inefficiency is not helpful. So I'm going to ask you to do that, as like I said here, like assign pages to problems. Yeah, does that make sense? I mean, I guess it won't make sense till you actually like do it, but hopefully that makes some sort of abstract sense. So good. All right. Cool. So then, yeah, so it shouldn't be, hopefully, you know, the first, it always takes a little bit to work some kinks out to get used to uploading these assignments and stuff. But I also have built into the problem sets a 48-hour grace period. So like they're due, like the problem sets due Tuesday night at 11. But there's like a late period that you can turn it in for the next 48 hours. I give you like 48 hours more. And that's like just if you're having a bad week or you can't get the assignment to upload or something that you have some more time. I'll ask you to like, and that'll be true for like the Friday problem set. I'll give you 48 hours on that also, or maybe, yeah, just Sunday at 5 or something like that. So I'll give like these 48-hour grace periods on the problem sets. I guess I just would say like, please don't get in the habit of just always using it, because then you're just getting sort of behind the class. And if you use it here and there, I won't say anything, but I can see obviously who turns stuff in. Well, what time, there's like a timestamp when you turn stuff in. So like, if you're doing it every time, I might like talk to you like, what's going on? Can we get you back on track? You know, but it's there just as an extra bit of flexibility. Like if you're just, for some week, it's just not a good week for you to get the problem set in on time. Okay, so good. Hopefully that's self-explanatory. And it does say, it's funny because it says late if you turn it in during the like 48-hour late period. And some students find that very upsetting that it says late, but I won't count any of it. There's no points deducted unless you start doing it every time for like, you know, 6 problem sets in a row. You're always turning it in like the last second of the late period. Then I'll start to be like, what's going on? Okay. Yeah, I think that's all the logistical stuff I had to say. Are there any questions about anything? Try to watch the chat also. Okay. Oh, I need my iPad actually. So let me, what I want to talk about today is surfaces. So we did some stuff with like getting used to 3D space on Wednesday, right? And we did that group work handout. Let me start a new notes page on here. I'm actually going to be showing you stuff in Mathematica today, which is this this like online, not online, this like program that's like a visualization system. So that lets us look at surfaces and stuff. But I need to write some stuff down first. So sorry, okay, share iPad. Okay. So people can see me writing. Yes, awesome, thank you. So we're going to talk about surfaces. Basically, we're trying to do the analog of, you know, y equals f of x in 2D. Right, so we're used to y equals f of x in the plane, and so we sort of, you have, I think I mentioned this maybe on Monday, like you have a really a lot of experience now with equations in the plane, and you know lots of functions, you know what x squared looks like, you know what powers of x look like, you know what sine and cosine look like, you know what exponential function, logarithmic function, you know, like you sort of know a lot of graphs, right? So those are, so y equals f of x, you have a lot of experience with, but z equals f of xy, we have almost no experience with, unless, I don't know, maybe you've been doing this just for fun for a couple of years, I don't know. So you probably don't have, I shouldn't say you definitely don't, you probably don't have a lot of experience with these. So let's just start with an example. And I think I mentioned, this is the example I mentioned, and then, but we'll do lots more examples. So One example I sort of mentioned to you on, I don't know, Monday, I think, was z equals x squared plus y squared. So I claimed this was like a bowl shape. But, the question is, what does the graph look like? Like, how do we know that? So what does the graph in 3D look like? And I think, again, maybe I made this point in class like Monday, but look, it can be sort of fancy with this. So here's your X, Y, Z space. I could pick a point in the plane, like, let's say I picked like, it's never works when I want to. If you hold down with notability, it's supposed to make a straight line. There you go. So let's say that's x equals 2, and that's y equals 1. So here is like x equals 2. Here is y equals 1. So this is the point 2, 1, 0. And if you plug that in, right, like when say x equals 2, y equals 1, then z equals 2 squared plus 1 squared, which is 5, right? And so that means up at height 5, so that's supposed to be through that point. So like up at height 5, there's this point in space that lies on the graph. This is like the point 2, 1, 5 lies on the graph. Of z equals x squared plus y squared, right? And you could do this sort of for every point in the xy plane. I can do this. We can start plugging in every point and see how high the point on the graph is, and then just start like placing those in space. I mean, if you think about that, that's what you did again with the analog with y equals f of x. If you have no idea what a graph looks like, you just start plugging in some x values and plotting the points, right? And that's how you start to get a sense of what the graph looks like. You do the same thing with graphs in 3D, but it's harder to draw, right? Like I can't really draw it that well. So I guess if you could like stand in a room and like suspend like Christmas ornaments from different heights at the right points and try to start to see what the surface would look like. But okay, but so we can plot points, but I guess what I'm trying to say is that like we can plot points in space, but that's a lot of work, and it's not necessarily clear how it's not necessarily helpful because it's kind of hard to see things in 3D. So instead, what we do, and you'll see this as a theme of the course, we're going to piggyback on our knowledge of 2D as much as possible. Like, we're just going to always exploit our knowledge if we can. So instead, one of the first things we're going to do is we'll look at what are called cross sections. Cross sections of the graph. Seems important enough to be like, let me put a little box around that. Cross sections of the graph. So what does that mean? What it means is you set x equals constant or y equals constant. So like, because that's kind of like a slice. Like if I look at all the points where x is 0, say, if I just set x equal to 0. So these are these are what are called x equals constant or y equals constant slices. So for example, if x equals 0, think about what that means up here in this picture, right? It means that we're in the YZ plane, right? When x is 0, that means we're kind of living in this thing right here. So I guess I should say A, we're in the YZ plane. And B, Z equals x squared plus y squared just becomes Z equals y squared. Right, because x is 0, so you plug in 0 and you just get Z equals y squared. And so this is a slice of the graph, basically. We're just like looking, and in fact, I could try to draw that again. So like, that wasn't straight perpendicular. Okay, so like, because this is y and this is that's x and this is z right here, that means that like, you know, we have some slice that's like, it's basically in the YZ plane, and we know what z equals y squared looks like in the YZ plane, right? Like, you know, that's just the standard parabola. I mean, the variables are different names, but you know that like sort of in this plane, you're going to have this parabola like this. That's like in the, not sure how to like make it more clear, but it's like in this little like plane right here. We've got, it's like that slice, right? We've got this parabola living in the graph. Does that make sense to everyone? So that's part of the graph. I mean, it's, we got to do this for a bunch of different slices, but that's part of the graph. Similarly, if y equals 0, we're in the xz plane, right? And b z equals x squared plus y squared, which is just x squared now. And so this is going to be harder to draw, but you know, we've got some sort of like something like this is kind of, is that making sense for like that slice there? It's like, it's kind of, I'm trying to do something that's like the XZ plane. And in that, we'll see something like, this is where it gets ugly. And this is why it's hard to draw in. This is a bad idea, I think, but we'll get some sort of like parabola, but that's now in that, in this green thing, in this like in the XZ plane. So we get a parabola that way too, right? It's a little bit, if that is impenetrable to you, just you don't have to draw that part of the picture if that's, sorry, that's a little bit hard to see, but in general, so we can just take slices. So and we want to take more than one slice. So like so let me put, maybe I'll put this off to the side here for a second. And in fact, I'm feeling like sort of guilty, like this is just not a good picture. Let me just, oh no. Okay. Trying to only erase things that I want to erase. Well, now that I erased half my graph. Okay. So let me try that. I don't know. I just feel like that's not even, that was probably more confusing than helpful. So let me just draw this back here. Okay. So that was that slice there. But we can take other x equals constant slices or other y equals constant slices. So like if x equals 1, first, we're in a plane. There's a plane. There's a plane x equals 1, right? which is sort of parallel to the YZ plane. There's another vertical plane, all the points where x equals 1, because the YZ plane is all the points where x equals 0. So the plane x equals 1 is all the points. It's another plane that's sort of parallel and vertical. It's another slice, you know. It's sort of a slice like here, right? If that's this sort of the center. So that's x equals 1. So again, A, we're in a plane parallel to the YZ plane. And 2, we're now z equals x squared plus y squared becomes z equals 1 plus y squared. So that slice is also a parabola, but it's shifted up 1. I'm going to show you some visualization software that will make this all a lot, hopefully, cleaner. But shift it up. And then like, we could just keep going. Like if x equals 2, we get z equals 4 plus y squared. Right, so that's another parabola, but shifted up. And then shifted up 4, and when x is 3, we get 9 plus y squared. So it's shifted up by 9, etc. Actually, I could have even said plus or minus 1 here. Like, I guess it's not in the plane. It was still in the plane parallel to the YZ plane. If it's minus 1, but it's on the other side. Right. So x equals plus or minus 2. We get that. And etc. We could keep making slices. And then maybe what we do is we try to reassemble them in our heads in 3D, which is not easy necessarily, but we start to get a sense of the surface. Are there any questions about just that part of it, that we're just basically going to be slicing either x equals constant or y equals constant? All right. I'm going to switch to this program called Mathematica, which at some point we'll sit down and actually do in a lab a little bit just to play with. But let me just show you a sense of what I'm talking about. So actually, it doesn't really matter that much here, but I just realized I was talking about x equals constant. So don't worry too much about the syntax of all these commands. I'm not going to go too far into it, but just saying that this is saying that we're going to plot x squared plus y squared for y going from -5 to 5 for different values of x. So like here, I can make this bigger. People can see this. Yes. Thumbs up. Okay. Thank you. So like here, when y was 0, or sorry, when x is 0, we get this parabola of just this is y equals x squared. When x is 1, it's just moved up a tiny bit. When x is 2, it's moved up a tiny bit to 4. When x is 3, it's moved up to 9, and so on. The thing that's cool about this is this software Mathematica. By the way, you can get this software. It's like accessible to students. You have to like ask for a license and then download it. Although I think there's some iPad version, but it's pretty limited. So this is mainly for like on a computer. The cool thing about this is that you can play this like a movie. So I'm going from -5 to 5, like x going from -5 to 5, and we get these like parabolas. And so we're seeing these slices of this surface if we do this, right? So we get these parabolas that go down and then up. Okay, so these are still 2D, but it's at least kind of compelling, maybe, right? You can sort of see what's going on. I have something fancier, which I can show you. Don't worry too much about all this code yet. So these are 3D. It's cool. You can do like 3D plots, but I'm actually plotting, it's kind of hard to say, but I'm plotting the points x comma y comma x squared plus y squared, but now I'm fixing an x down here. Again, it's sort of an x equals constant slice and letting y change. Again, don't worry too much about all this syntax, but you can get something similar now if x is 0, and you can sort of see the axes. So the x-axis, one thing I wish Mathematica did more easily was actually draw the axes in the picture. So, but hopefully you can see that. And if you have any questions, if I'm doing something that seems really confusing to you, please just pipe up or put something in the chat. But like now, so okay, so this is a little different from the perspective we're used to, because the x-axis is going left to right sort of here. Z is going up and down. The cool thing about Mathematica is this does this in 3D, and you can sort of like drag it around and look at it. So I think our perspective that we're more used to is like this, because the x-axis, so like there's the x-axis, this is kind of the x-axis, y-axis, z-axis that we're more used to, right? And this is what I was saying. I think, you know, I'm letting y go from -5 to 5, but z equals 0 is down here and then up to 25. So this is the problem I was talking about that I drew in the picture. Does that make sense? And now if I switch, if I switch to say x equals 2. Okay, well, it moved, and it's hard to tell, but now it's, yeah, I should have actually done this when x was 0. Like, so when x is 0, see, it's in this, you can see x is 0, so it's living in this plane. This is the YZ plane that we're sort of looking at edge on right now. And it's this parabola shape. If x is 2, maybe I'll look at it edge on so we can, if I change this to x equals 2, see, it moved over there to x equals 2. But this was the 4 plus y squared parabola that we had, right? And the cool thing is I can play this like a movie. If I go to there's a slider, you can slide, or you can like play a movie, which is kind of cool. Like, this is what the slices look like. So we're assembling this from slices, right? So that's sort of end on, but I can, oh, actually it doesn't like when I try to turn it while it's playing. It doesn't seem to play nice, but I can turn it a little bit more, and it's like that. Can you guys see that? So this is like part of the surface we're getting. And actually, I can actually put in the surface now. So there is, I claim the surface, and you can sort of believe it if you play the movie of the x. This is the x equals constant cross sections. Oh, I need to turn it again so the x-axis faces the way we're used to. Sorry, getting this to orient correctly is kind of a game in itself. But yeah, so do you see how those are like kind of, it's kind of tracing out the surface, almost like a movie? Does that make sense? So it's kind of cool. This is sort of a way that we have to build surfaces, is to try to look at cross sections and try to like imagine. I mean, you can try to do that up here just from this picture. Also, you know, you can try to see, oh, if I'm slicing a bowl vertically, it's going to look, the slices are going to look like this, right? Because I mean, you really need the software to be able to look at the 3D picture. So, but I think this is kind of cool. And then there's also, oh, it just occurred to me that I could have done. Oh, how crazy do I want to be with this? No, not that crazy. Okay, so I could have done this also if I switch my X and Y here. So actually, I think I have the code somewhere else, but let me just do it here. So if I now take the Y equals constant cross sections, and I'm going to make them maybe blue now. This should be very similar, right? So now, again, let me turn this so it's kind of how we're used to. X pointing out at our face and Y and Z there. So now if I play this, it is really it's those cross sections. Those are perpendicular to the red ones. I don't think I have a good way, at least off the top of my head, to show both simultaneously, but there are ways to do that. But yeah, do you see what I'm getting at here? So it's like we get the cross sections of parabolas in one direction when X is constant. When Y equals constant, the cross sections are parabolas in another direction. And so the way they combine is to make this bowl shape. So do we now believe that X squared plus Y squared is a bowl shape? Feels reasonable. Okay. Cool. So that's an example we're going to use a lot. Let's think about another example. Instead of X squared plus Y squared, let's look at X squared minus Y squared. So let's see if I did this. So now I have X squared, again, don't worry too much about all this index, but I now have X squared minus Y squared there instead of X squared plus Y squared. So now this is X equals constant cross sections, right? There's an X right, it might be hard to see, but there's an X right there. If X is constant, like if X is 0, we get minus Y squared. If X is 1, we get 1 minus Y squared. If X is 2, we get 4 minus Y squared. Can someone tell me what kind of shapes those are and how it's different from the previous example?
Is it just an upside down parabola?
Yeah, they're upside down parabolas now, right? So again, let me turn this. X-axis is there. There we go. So those are upside down parabolas. Actually, sorry, I think I wanted, well, okay. Yeah, sorry. Okay, and then if I switch X and Y, so now I'm going to look at Y equals constant cross sections, and again, I'm going to change them to be blue. Okay, let me change the picture. So I'm trying to get it look like the picture was before. So before we had upside down parabolas, as Zach mentioned, going kind of towards us, right? Like upside down parabolas kind of moving forward and away from us. So if we take X squared minus Y squared and we let Y be constant, those are still upward facing parabolas, right? I need to change, wait, I need to change something. This is kind of silly, sorry. I just want to change the Z range that's showing here. Sorry, that was kind of a random thing I did. Yeah, okay, so now, where did I go? Okay, so yeah, let me do this one more time, switching the X and the Y. Let me switch the X and the Y back. So what I was saying is like, right, so we get these parabolas downward facing sort of, oops, it's still blue. I didn't turn it back to red. Every time I have to reset the whole thing. Okay, so each time I'm just trying to drag it so it's kind of the same orientation. Right, so we get these parabolas kind of coming towards us, I guess, from because x is going from -5 to 5, right? So we get these downward facing parabolas coming towards us. Really doesn't want to move when the movie's running. Sort of going this way, right? And then if we change x and y, actually, maybe I'll just do it as a whole separate. Separate thing. So if we change x and y, let's start with something more slick. And let me again reorient this kind of so it's a similar orientation to that. Okay, so here, like again, I said, these are these slices this way, the downward facing parabolas. Oh, I didn't change these to red, not to blue. Okay, and reorient. Trying to make it look as similar as possible. Okay, so we have those red parabolas going down. Now we have these blue parabolas going up, but they're more like left to right slices now, right? Because we're doing y equals constant. Can I play both videos? Can I play both animations simultaneously? There's that one. And then there's that one. And one thing you want to sort of try to convince yourself is that they fit together, right? Like these parabolas going down, like these both are supposed to live inside the same surface. So if you think about perpendicular to these or these blue parabolas, then it's maybe hopefully should make some sense that like, yeah, these parabolas are sort of going down this way, but like if you think about just following one point on one of these red parabolas, it itself is making a upward facing parabola. Does that make sense? Like if I'm just like keeping the same point, it's going down and then it's going up. So because I'm trying to think about the blue being perpendicular to the red here. So like if you're following the same point, like maybe the top of the parabola, it's itself making an upward, that's tracing out an upward facing parabola. And that's like if I pause this like near 0, that's kind of this what the top of the red parabolas is tracing out, something like that. I guess I can make it actually 0. Does that all make sense? So then you can combine everything and try to get a sense of what the graph looks like. I mean, do people have a, can you picture? Maybe I should just be like, you know, try in your head to picture what the total surface looks like. I put that graph too. It looks like, oh crap, why do I have, sorry, I need to change the, where is it? Oh no, I did do that. I don't know why it looks a little funky. Why is it from, sorry, this is supposed to have Z go from, well, this is what the graph, so this is what the combined graph looks like, which maybe you can sort of see now from the movies. Like in one direction, if you slice in one direction, we get these upward facing parabolas. If you slice in another direction, we get these downward facing parabolas. And you get this has a name. It's called a saddle. And it sort of makes sense, right? It looks like a saddle. So, oh no, this is fixed now somehow. Okay. Oh, I see why. Okay, so now if we play the red, oh wait, change orientation. So the x-axis is pointing more towards us. Okay, so now we play the red video and we see we play the x equals constant slices and we have these red downward facing parabolas. And the same thing with, if I change this to graph 2 and I move, reorient. So here we have these parabolas facing down, and here we have these parabolas going up. Cool. So this is a way we're going to try to figure out surfaces. I mean, you just kind of can start to remember, okay, so I've got in one direction, if you just think about in x squared minus y squared, setting x equals constant, you get downward facing parabolas in one direction, upward facing parabolas in another. You can sort of see how they trace out, and you can sort of try to get used to the fact that that's going to make altogether this saddle shape. Okay, makes sense. We can get, I mean, we can certainly get more crazy about what our functions are, but this is a place to start, these cross sections. So we've sliced vertically in these two different ways, right? But we could also try to slice horizontally. And so maybe I'll go back to the iPad for a minute. So yeah, so we have vertical cross. So we have the vertical cross sections. That's what we were talking about here, right? What about horizontal slices? We could also try to think of a graph by slicing horizontally. So here, I mean, z equals constant, right? Because if z is constant, then we're just always at the same height. So for example, when for z equals x squared plus y squared, if right, if z is constant, if z is like 4, we get 4 equals x squared plus y squared. And you think about the bowl shape, if you slice it horizontally, what kind of slice, what are the slices going to look like now? I slice a bowl horizontally.
Circles.
Circles. So, and in fact, that's exactly what this is, right? This is a circle. That's an equation of a circle of radius 2. So this is a circle of radius 2. In the plane z equals 4, right? So at height 4. That's what we have. And so when z is 1, z is 3, we can imagine setting z equals constant. Now it just turns out those aren't, we don't call those cross sections. We call those contours or level curves. These are called contours or level curves. And we can play the same game where we set z equal to various constants and draw the level curves, right? Yeah. So now the thing that we do here, though, it's a little bit often different. This is a completely different way to visualize. This can give us a completely different way to visualize. The function. Let me go back to the Mathematica. So you guys are seeing the Mathematica again, right? Oh crap, did I lose my code? Oh no, sorry, let me copy some code from somewhere else. Okay, so if we think about plotting all of these, but instead of, we could do them in space again and sort of see how the surface forms, but they're all equations in x and y. So we can actually think about just plotting them all in the xy plane. So let me just show you what we get. Whoa, what's going on here? Okay. So here, if you, this is called a contour plot, and we're going to talk about these, but this is the bowl shape again, but now we're looking at it from above, kind of, right? In fact, if I just go back to the bowl, oh, I did the opacity thing. Hold on. Sorry. I know this looks annoying, but let me go back to the bowl for a second, the 3D bowl. Let's not worry about the cross sections for a moment. Let me change a couple of things here. I want the mesh back. Let's try this. Okay, so this gives us the bowl. And actually, this, if you just do, oh, I changed that to graph. Okay, well, I messed up something. Okay. So you could actually see all three types of slices here because it's a little bit busy, the picture, but you can sort of see the parabolas that are like either the x equals constant or y equals constant slices. But now you can also see the z equals constant slices, which are these circles we were talking about, right? And if you actually just take a direct top view, then you can sort of see it's like, oh, I have a bunch of circles and they're getting farther out as z gets higher. And this is kind of just smushing this all down into a 2D picture. And now this is labeled like this is the slice at height 5. This is the level curve, I should say, at height 5. This is the level curve at height 10. And they do get closer to each other, which is an interesting thing to think about, like, because it's going up by 5. It looks like the height's going up by 5 each time. But you're just increasing, like when z was 4, we got 4 equals x squared plus y squared, which was radius square root of 4. That was radius 2. If we go to height 9, we get radius 3. If we go to height 16, we get radius 4. So if we want, like, we have to go higher each time to get the same growth in the radius. If that makes sense. So that's why these are getting closer together. But that makes sense also for the bowl shape. If it's going up and getting steeper on the sides, then these should be getting similar. These should be getting closer together as we go away from the origin. Now, this should look familiar to you. You may do a lot of hiking, like when you're trying to like set up a route for your hike or something. Like, what kind of map do you look at? Like, what kind of map does this remind you of?
Topograph.
Yeah, a topographic map, right? That's kind of like, it's like if you want to look like and see how some like mountains and elevations and stuff are changing, like that is a way to get a 2D rendering of a 3D map, is to just like draw all the points at the same height and then label that with the height. And that's really what we're doing here. That's what a contour, this is actually called a contour plot, which is right there. But so when we look at the contours and we put them all together, you can sort of, this is another way to try to recreate the graph in your head. If I change this to x squared minus y squared, now this is interesting. Does this feel right? So height 0 is actually these two lines. And then as we go sort of like east-west, we increase, you know, we're increasing in elevation. If you think about these as like elevation numbers. And the minuses are partially obscured by the lines, but these have minuses, -5, -10, -15, -20. So as you go north and south, you go down. And can you in your head recreate the saddle picture from that? Like going 2 directions, we go up, other 2 directions, we go down. So I don't know if you can see me or just see the share, but like sort of like have something like that in my head. And do you sort of believe that that actually is something similar to this? Again, we could look at this. Actually, yeah, hold on, let me just take the graph. Again, sorry, I'm scrolling through and making it look, I'm sure it's, let me put the graph of x squared minus y squared here, but allow the mesh. Okay, so here is this saddle. If I again look from the top, okay, we can see this, the parabolas, the upward facing parabolas, the downward facing parabolas as slices, you know, in this mesh. And then if we look from the top, organizing, let's see, I have, sorry, it can be hard to keep. No. Yeah. If I look from the top view, yeah, it makes sense, right? That like the, you know, we're going up if we go east and west and down if we go north and south, right? And that's reflected there. Okay. So this is called a contour map. And so this is the main ways that we start to visualize surfaces, by vertical cross section, either x equals constant, y equals constant, or these horizontal cross sections, which we call contours or level curves. And those we can put together nicely into this contour map and actually get like a 2D, a 2D representation of a surface. Any questions about any of this? You guys are kind of quiet today. I appreciate the people who've been asking questions. I just kind of wanted to get you used to like some of these ideas. It should set you up well for all the homework, like I think the second section of the homework now. Otherwise, what we'll do is we'll just I'll probably on Monday do some more examples just to show you a few more examples, and start moving into like, we could do like more basic things like linear functions. Like these were both quadratic. I mean, again, you can do sort of slightly crazy things. You could do like, I could do sine x times sine of y or something like that. That's interesting, right? All of a sudden, what the hell's going on here? Sometimes figuring out the zero contour is interesting because you're setting the equation equal to 0. So if you set sine x times sine y equal to 0, then like that means one of them is 0. And sine x equals 0 every pi, you know, when x is pi, multiples of pi. So that's why when x is, it turns out these are x's, like you can actually see this is about, that's 2, that's 4. So this is about at pi. So you get these horizontal, you get these like lines. But then if you want all the points where it's 1, height 1, like sine x times sine y is 1, then you need x to be like pi over 2 and y to be pi over 2. So there's these like peaks in the middle here and so on. So you can sort of convince yourself of what's, of like, I mean, it said these curves, I have no idea, like sine x times sine y equals constant. Like these are weird. These are not circles. They're something else, but it's kind of fun to start playing with this. And like, I'll show you again a little, we might go to the lab a few times and try to do Mathematica together as a group. And like I said, you can also download this program on your computer yourself. And it's very friendly, like any command, like I keep see that like there's an eye right there. If I touch the eye, it actually gives me a whole page of like how everything works, and also it gives you sample code and all sorts of stuff. So like, and there's a lot of if you just happen to want to download Mathematica like over the weekend, that sounds like fun. There's a lot of documentation, and you can sort of do a lot. It's a very powerful program. We're just very scratching the surface of it, but yeah. And so we're doing a lot of this function visualization stuff, and then there's all these, but it does a lot more. So, and it's expensive, but it's free at Bowdoin, so because you have student site license. So. All right. In that case, I guess I will stop. I have office hours immediately right now, and I'll go over to the Gather. So a few of you have visited me there. So there's that link to the Gather on our main page below my office hours. But all right. Take care, guys. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.